Welcome to Lab Life with the Air Force Research Laboratory.
Hi, I'm Michelle.
And I'm Kenneth.
Hello, folks. Today we are joined by Dr. Robert Fugate to discuss his astounding career in physics, astrophotography, and how he gained the title Father of Laser Guide Star Adaptive Optics.
In 3, 2, 1.
Dr. Fugate, we're so excited to have you on the podcast today. Thanks for joining us.
Oh, it's exciting to be here.
And today we're going to start off our podcast a little bit differently. You have a recording that you captured at a young age that in a long roundabout way is why we're talking to you here today, because it sparked some curiosity to interest. Could you share that with us?
Sure.
So what did we just listen to?
That was Sputnik 1. I recorded it on my amateur radio receiver in 1957, in October, actually, of 1957, just after the launch. And it was broadcasting on set frequencies. It was really quite a smart move on the Soviets' part to put it out so that amateur radio operators all over the world could hear it.
That's amazing. So how did you originally get the idea to listen? Did you hear that it was going to be passing overhead, or was this more of just a interest that hopefully you could catch something when it did?
Oh, yeah. We were, when it happened, it was a big surprise. And I was like 13 years old, and I hung out with a bunch of my sort of nerdy friends, and we followed a lot of this sort of thing. In fact, you know, Arthur C. Clarke, who was a science fiction writer in 1945, he proposed the idea of geosynchronous satellites to broadcast TV signals. So we were aware of that. We were aware that you could launch a satellite and have it circle the Earth. So seeing and hearing Sputnik was just amazing, because here was some theoretical idea that had become reality. And hearing it in your radio as it went overhead, you know, it faded in, it was very weak, and then it got stronger, and then it got weak again. It was just very inspirational. And seeing it with your naked eye, you could see it with your naked eye in the right conditions, and you certainly see it in binoculars. It really had a huge impact on probably my entire career, my entire life.
I mean, I fully believe it. Hearing, like you'd mentioned, science fiction becomes science fact, especially within your lifetime, just seems like a lot of people just think like, oh no, I mean, flying cars, I mean, communicators, things that we see in like Star Trek is way off the future. But to see it happening already, and then, I mean, continuing from there, you're right, it has to be awe-inspiring and really get you inspired to join the career field. Like, hey, if they can do that, I would love to get myself up there too, or something I work on up there orbiting the planet. Like, how cool is that to motivate people in such a way?
Yeah, it was amazing. Our little group, there were 3 of us, and we immediately started trying to build rockets. And so, you know, we got pretty serious about it. And that was one of the impacts that happened right away was, you know, wow, maybe we ought to understand this stuff better.
So I'm glad you mentioned that. There's a very interesting anecdote you shared with us beforehand about these friends that you're working with to make your own rockets, and it involves rocket fuel, a skillet, and a fire. Do you mind sharing that story with us?
Okay. We read everything we could sort of get our hands on, and of course there wasn't any internet at the time, so it was all in books or magazines or whatever. And we figured out that if you took an aluminum tube, you could put rocket fuel in it by melting potassium nitrate and sugar in an electric skillet. So when my mom was at work, we got her skillet out and we took it in the backyard. And fortunately, we were smart enough to do this outside. And there's a very small range of temperature between when it kind of becomes a liquid and when it flashes and starts burning. And we figured we could use a candy thermometer to keep it, you know, in that range. But apparently the thermometer was not calibrated and things got out of hand and the whole skillet went up. And got all black, and we spent the rest of the afternoon trying to clean her skillet up so she wouldn't know what we'd been doing. Fortunately, we survived.
Yes, here to tell the story. I would not recommend if we do have anyone probably listening right now to try that in their backyard with a skillet, let alone children.
Yeah, that's right. Yeah, we probably shouldn't even be talking about this, but this was way before, the model rockets came along, and which are now quite safe and easy to use. And so it was back in the sort of pioneering days.
Well, honestly, somebody had to go ahead and do it and then help tell people, hey, we've tested this out. So for these new model rockets, I would try this avenue instead. So, I mean, it gives you a wealth of experience. And like you said here, I'm a cautionary tale for other folks looking to do the same. So glad it all worked out, and glad you guys still had such a cool way to piece together the mystery of how to build it, though. It's cool that you guys actually put in the research and the legwork to almost make something happen.
Yeah, we actually, there's a movie called October Sky. What we were doing was pretty much parallel to what's shown in that movie. Homer Hickam was the principal in the movie, and I actually met Homer Hickam, and he wrote a book about it, and I have his autograph in the book. And but it mimicked what we were doing almost exactly. We had a machinist make some nozzles out of steel, and we threaded those into these aluminum pipes, and we finally got the fuel thing working right. And we actually fired off some rockets that disappeared. We couldn't find them. It was a great fun time. And of course, a lot of this we were kind of doing like a lot of kids do without our parents' knowledge, and in semi-secret locations. And I can imagine today, with all the communications and connectivity that kids have, that's probably goes on even more.
Well, except that they would have put their attempted rocket launch on TikTok and probably gone viral. So
Right.
Or another social media platform.
There you
go. You ended up studying physics in college. What was your work like there?
My parents worked at the National Cash Register Company in Dayton, Ohio, and they had a 5-year actually, co-op scholarship that they awarded to an offspring of an employee, basically every year, to the University of Cincinnati. It was a great scholarship because it provided all expenses, provided a intern job, but I turned it down because I was more interested in what the fundamental things in the world were than the engineering aspects. So I, just like back when I was getting interested in ham radio from my father, I liked building radios and stuff, but what really fascinated me was how you could bounce this thing called an electromagnetic wave off the Earth and the atmosphere, the ionosphere, and have it travel, all the way around the world. I wanted to do physics as opposed to engineering, and I really was fascinated by some of the things going on at Case Institute of Technology in Cleveland. So I ended up there. And I was fortunate to do a senior thesis while I was there, and actually published the results in a refereed journal as a senior. And also the school had a telescope out east of Cleveland, a 9.5-inch refractor that had been built in the 1800s, late 1800s, and was a student telescope. And it was part of the Werner Swayze Observatory. So I spent a lot of time out there working on that telescope and learning how to use it and making images of the night sky.
So during that time when you were still really getting used to using larger telescopes and using an observatory, what were some of the cooler findings you had, or cool moments that really connected you with the night sky, excuse me?
Well, I don't know that, there wasn't any significant amount of research. It was just learning how to put a piece of film at the focus of the telescope and expose it properly, and how to keep the telescope tracking and not wobbling on the sky so that the stars would be pinpoint in shape and not trailed, and things like that. Having sort of hands-on that equipment and trying to make it work and understand how it worked and what its problems were was really what motivated me.
Yeah, put a lot of those fundamentals in your mind at the early stages there to make sure you could work on a lot of the higher range stuff we'll see, well, down the range here soon. Which, speaking of, going along your the training you had or kind of the schooling, we know you did graduate school at Iowa State next. What work did you do there? Kind of how did that continue your career in astronomy?
Actually, it had little to nothing to do with astronomy, but I went to Iowa State because my thesis advisor, when I was a senior, suggested that I go work for a particular fellow at Iowa State, Clayton Swenson, because he said he was really good at training experimental physicists, and you need to go there and work for him. It also turns out that I applied for and won a NASA fellowship for my graduate school work, and so it was kind of a no-brainer. I got into school, I got the fellowship, I had a recommendation for Professor Swenson. And so I started, the summer I graduated from undergraduate school, I moved to Iowa. Well, the first thing that happened was I got married. Then I moved to Iowa. A lot of stuff going on. It was a very useful experience working for him because I did a thesis in low temperature, high pressure physics. And it had to do with the thermodynamics of the solid, kind of an oxymoron, solid noble gases, in this case neon, and its isotopes. And I measured the constant volume specific heat, which was an experiment that involved temperatures near absolute zero and pressures of 200,000 psi. And I built all that equipment because that's what he insisted. And he said, if you're going to someday direct research, you really need to learn how to do it. And that was a great lesson for me in my career because it paid dividends the rest of my career.
Yeah, I'm just trying to wrap my head around the idea of you said you built, or I really gathered a lot of these experimentation devices and a means to actively go into your thesis. Like, what actually went into building this? Was it a team effort or really just you kind of solo working at a lot of these devices?
No, it was just me working. I learned all kinds of techniques. I learned how to work in a machine shop. I learned how to silver solder. I learned high vacuum systems. So today, even now, that pays off because if I need to do some kind of plumbing repair in my house, it's a piece of cake. The students that worked for Professor Swenson, we worked in the basement of the physics building because it was low temperature physics and you want to minimize vibrations and stuff. But we had a reputation that if you really wanted to get something done, you would come and ask some of us because we had hands-on experience about how to do things. When we built all of our instrumentation, we pretty much did it all from scratch, except for a few essential high precision instruments. We built all our own electronics as well. So it was a great education in terms of, as he said, learning how to do research.
And what's really cool there too is the fact that, like you mentioned, being part of every step of the process, building the electronics, soldering everything, knowing how everything works in a very innate manner means when things go wrong, even later down the line, you'll be like, wait a minute, I built one of these before. I think I know how to fix this, or at least I think I know what may be causing this error. So like you said, this hands-on approach, which we've seen from the beginning with the rocket fuel work all the way till now, like really helped shape your career to be prepared for, well, a lot.
Yeah, that's right. When something is not quite right, when you have a problem, when you're trying to do a research project, you always have a problem. And I think what I learned in graduate school was techniques for how to solve those problems, whatever they are, in whatever field they are. It's sort of a general approach. So it was great advice from my thesis advisor to work for Professor Swenson. He was a formal sort of guy. He was educated at Oxford in England, and he maintained sort of a formal relationship with his students. I think that's a lot different these days, but I never really knew what he thought of me and my work as I went along for nearly 4 years working with him. But in the end, after I've passed my final oral exam, he told me, the project you did was probably the most difficult of any of my students. And I think there are a lot of my students that couldn't have been as successful as you were. So that was very gratifying to hear from him. And he passed away a couple of years ago, but we maintained our friendship and communication right up until the end.
Yeah, to be a physicist at that level and to have somebody like you mentioned give you that accolade and be a mentor and like you mentioned a colleague and a constituent that you could like rely on and talk to for so many years. I mean, that's indispensable. So, I mean, amazing that that all worked out really well for you and that you really found a friend there.
It was kind of a golden era for me.
So speaking of golden era, we know that shortly after this, you did connect with AFRL, our team, I should say, the Air Force Research Laboratory. Can you kind of go into that story and what happened there?
Well, when I graduated, coming up to graduation, it was kind of that was in 1970, and it was kind of a PhD physicists were kind of a glut on the market. What I really wanted to do was stay in academia and be a teacher, but there were just no positions and very few in industry. So it turns out there was a really sharp fellow in the Air Force, and he worked at the time, what was called the Foreign Technology Division in Dayton at Wright-Patterson. That's the same group that I think is now NAIC, and I'm not National something Aerospace Intelligence Center. I'm not sure I've got the acronym correct.
No, you've got it. We colloquially call it NASIC.
NASIC, yes. And so he worked there, and he realized that there were a lot of PhDs out there looking for jobs. And so he decided to create 2 positions for PhDs. Now, I'm not quite sure how you specifically say that you need a PhD to fill a position, but somehow he had these 2 positions. And the way I found out about it is what's so funny. My wife's mother was a hairdresser, and one of her clients was the wife of this fellow, Elmon Decker at FTD. And she knew that he had created these positions because, he was telling her about it. So when my wife's mother was doing her hair, there was chit chat, and she said, "Boy, my son-in-law is having a hard time finding a job." And that's how the connection got made. And I got the contact information. I was invited to come out for interviews and give a talk. And they made me a job offer, which I accepted. So in December of 1970, I started working at the Foreign Technology Division. But unfortunately, shortly thereafter, I was caught up in a reduction in force action, and I got bumped by, a senior person with seniority. But I had actually been working over at the avionics lab in a laboratory, knowing me wanting to actually get in the lab. So turns out they had a way to have overhires at the avionics lab. So I got a job over there. And I finally got some tenure and then eventually transferred out to Kirtland. So at any rate, talk to your hairdresser about things and that'll help others.
Everyone's in the network. You never know who knows someone.
Yeah, that's right.
Well, then if we jump out to, the Albuquerque, New Mexico area, for our listeners, that's where Kirtland Air Force Base is. And we really want to focus in on the work that you've done that is now known as the Starfire Optical Range. What is the Starfire Optical Range?
The Starfire Optical Range, or the SOR as it's called, is an optical test facility, and it's located in a remote part of Kirtland Air Force Base. Kirtland is a very large base. It's, somebody once told me it's, bigger than the District of Columbia. Like a lot of bases out west, it's large, and so it has some remote areas. It is an area where research is done to investigate new methods for imaging satellites. And this all got started back during the Cold War when the Russians, at that time the Soviets, were launching a new satellite every 3 or 4 days. And most of them had some sort of military mission. Well, you can imagine that the US was very interested in understanding and learning what was going on, what they were doing in space. And one way to do that is to try to get a picture or a view of what the shape of the satellite is and what it has on it and what it might be intended for. And so the avionics lab actually had a facility in southern New Mexico at Cloudcroft, 48-inch telescope that they used to try to image satellites. It actually had a mode in which a person could ride on the telescope, look through an eyepiece under a great magnification, and try to discern what the satellite looked like. The problem was the atmosphere. The atmosphere causes images, highly magnified images of objects in space, like astronomical objects, or in this case, satellites, to be blurry. One extreme case of that is if you've ever been driving along the road in a hot summer day, you can see heat waves coming up off the road. This is the kind of thing that causes blurry images in telescopes, large apertures and high magnification. So at the SOR, the work continued basically once this idea of adaptive optics came into existence to try and fix this, to form images of satellites. Kind of a long explanation, but the SOR is basically an optical research and test facility for doing what's now called space domain awareness.
So you just touched on something big there that folks within the know have obviously heard before. Many of our listeners may be unfamiliar. So you were mentioning and talking about adaptive optics. And from what we've heard in the community and talked to a lot of folks, you've been called the father of laser guide star adaptive optics. So with that sentence in mind, what exactly is adaptive optics, and how has the work impacted, how's that technology really impacted the world of astronomy?
So the idea of adaptive optics is, if I could somehow measure the distortion of a light wave that has just come through the atmosphere from an object in space, and I'll try to explain that a little more in a minute. If I could somehow measure what that distortion is, and oh, by the way, that distortion changes hundreds of times every second. So it's a daunting task to actually make an instantaneous measurement of what it is at this instant. And then if I could somehow impart that distortion on a mirror, think of it as a piece of rubber that you change the shape of. If I could get the distortion that exists because of the atmospheric turbulence on the mirror, then when the wave reflects off the mirror, the distortion is removed. So I have to match up all the bumps and valleys just exactly right on the wavefront in order to remove it. And so that's the idea of adaptive optics. And that process involves analyzing the light coming from the object you're trying to image, and then controlling a mirror that can put the inverse of that distortion on the mirror so that you can remove it. And then the light that goes into your camera off the mirror is essentially restored to what it was like before it entered the atmosphere. The problem is the distortion is caused by different regions in the atmosphere that have different temperatures. And that causes the light to travel at different speeds. The speed of light in a medium is governed by something called the refractive index. So like glass, for instance, has a refractive index of like 1.5, whereas air has a refractive index of like 1. And a vacuum has a refractive index of exactly 1. So as the light travels into media of different refractive indices, it slows down. If the refractive index gets larger, the light moves slower. So in the air, if the light enters a pocket of air that has a different temperature than its neighbor, it may get slowed down. And so one part of the wavefront gets ahead of another part, and that creates a distortion, a crinkliness, a uneven surface, a non-flat surface. the adaptive optics process tries to measure that crinkliness and put the inverse of that on the deformable mirror, a mirror whose surface you can control by electrical signals and correct it. So I don't know if that is too complicated an explanation, but that's kind of how adaptive optics work. You measure the distortion, and then you control a mirror that puts the inverse of that distortion on the mirror for that instant and correct it.
Well, for some of our listeners, that might have been at a 101 level. For me, it felt like a 103, but I'm tracking that this was a huge deal. I think that Kenneth had a really great analogy when we first met you and talked to you about, this advancement in adaptive optics really wasn't just an inflection point. It really revolutionized of the capabilities that our country had. Ken, you're the history major. What did you reckon it to?
So we were talking to another constituent of yours, Dr. Fugate, Dr. Drummond, and the way he put it was this discovery was one of the biggest things that's happened in astronomy in the past 400 years. And I was like, so that means he's like the modern day Galileo? And he was like, yeah, kind of. So I want to touch back with what we mentioned. So again, you have that name, the father of laser guide star adaptive optics. What earned that title? What work did you do directly with this to earn that honorific?
Yeah, I think the key there is laser guide star. And while the idea of adaptive optics was originally introduced by an astronomer, a guy named Horace Babcock, who worked at the Palomar Observatory in a paper back in 1955, it wasn't exactly what we see now in a modern day adaptive optics system, and in fact, we didn't have the technology at that time to implement his idea. But his idea was just what I described, measuring the distortion and then deforming a mirror to correct it. And we just didn't have the wherewithal to do it. But 20 years or so later, the technology had developed to the point where it could support that. The issue is in the measurement. If the object you're looking at is very faint, and astronomers, of course, are really interested in really faint objects, there isn't enough light to make a measurement in time to make the correction. What I mean is you have to collect, for a very faint object, you would have to integrate long enough to make the measurement. And while you're integrating over that period of time, the atmosphere is changing. So you haven't been able to keep up with the changes and the system won't work. So what you need is an artificial source in the sky that's in the same direction of the object that you're trying to look at. And that artificial source is bright enough that you can make the atmospheric distortion measurement with it instead of the object you're trying to image. And so that's the idea of the laser guide star. You shine a laser in the sky, some of the light gets scattered back into your telescope from some range. And there's actually two methods for making a laser guide star. One is from Rayleigh scattering. This is scattering off of the molecules in the air, the oxygen and nitrogen in the air. And this process is actually what makes the sky blue. Rayleigh scattering scatters, the blue light, and you see it all over the sky. The other approach is to use this layer of sodium atoms that's at 90 kilometers above the Earth and is deposited by grain-sized meteors that constantly bombard the Earth. The Earth picks up several hundred tons of meteor material every year or every month, or it's a lot of stuff coming in because of the gravitational attraction. So as it burns up, one of the constituents of these meteors is sodium. Sodium is light, relatively speaking, and there's nothing else up in the upper atmosphere for it to react with, so it just hangs out. And you can actually see the sodium glow in pictures from the space station. It's a thin orange band above the surface of the Earth, a yellow band of light. So if we could shine a laser into those sodium atoms and make them glow, then we could use the glow from those sodium atoms as a guide star in order to run our adaptive optics. And that's the technology that is now being used by astronomers. So my connection with all this is I did the very first experiment using a laser using the Rayleigh scattering approach to demonstrate that, yes, you could shine a laser in the sky, you could focus it, you could measure the light coming back from some distance, about 15 kilometers, into your telescope and actually measure the atmospheric distortion with that laser spot. And it does very closely approximate the information I would get if I had light coming from a star. And in that very first experiment, we did it by, in fact, pointing a laser at the star Polaris, because we didn't have a gimbal telescope that we could, point anywhere in the sky. Instead, we had to use basically a nearly fixed star and point a flat mirror at that star so that we could make our comparative measurement between the laser and the star. And the time we did this, which was in 1983, all of this was classified. And it was being done under a project for DARPA, and they had classified all the technology, and it remained classified until 1991.
And to think that the North Star, the guiding star, was still there to do exactly that, and a lot of the experiments here is still really cool. Like basing a lot on what humans have been looking at for generations to help us kind of work on this adaptive guide star optics.
It all fell into place basically, and today all the large telescopes that are in use by astronomers are using this technology. It makes no sense really to build a very large telescope without it, because even if you have a 30-meter telescope and you basically would get the same blurry image that you get out of a 8-inch telescope, you just get that blurry image faster. And that doesn't really do you any good in terms of the science of trying to understand what's going on at the edge of the universe, where you need the resolution and the sensitivity. For instance, if you have a laser guide star on a large telescope, the sensitivity of the telescope, the amount of time it takes to get to a certain signal to noise ratio of a very faint target, that sensitivity increases as the fourth power of the diameter of the telescope if it's corrected with laser guide star adaptive optics. Otherwise, it's the square, just because it's just the area. So that is a huge, huge difference, and it's what makes building these extremely large telescopes physically viable and scientifically relevant. Otherwise, it makes little or no sense to do it.
And I want to go back real quick to 83, as you mentioned, when you were actively testing out the Rayleigh scattering and working on this laser guide star adaptive optics. Can we kind of go into your headspace? At that time, did you really feel like when you were here, like this is going to change a lot? Like this technology here is really going to change the game for us. Like, what was it like?
I knew that ultimately for the Air Force, for instance, we needed a 4-meter class telescope, and we needed a sodium laser guide star to correct that telescope. But I also knew, and it was my vision, that this would be a huge boon for astronomy. And because the astronomers on the ground have been plagued by atmospheric turbulence since the invention of the telescope. As Jack Drummond said, it's the biggest advance for them in 400 years. And that's why I worked so hard to get the information declassified. And we actually worked almost 2 years, and the sort of demise of the Soviet Union, I think, was what eventually enabled that and got this information out into the astronomy community. And we actually had at Kirtland, we had a big meeting after this was declassified, and the information was presented at the American Astronomical Society meeting in Seattle. We had a meeting at Kirtland, and we had 250 astronomers attend the meeting. And we had 4 nights running, we had tours at the Starfire Optical range of the Rayleigh Guide Star system in operation. It really kind of got the whole community going.
And speaking of the community and these advancements, so something more of just out of our curiosity and kind of help inform our listeners, can this technology be used to like check out and track exoplanets or even find habitable worlds for humanity to maybe settle later on in the future?
Yes, absolutely. There is high performance adaptive optics now being used on the largest telescopes to survey and directly image exoplanets. And furthermore, to measure using spectrometers the constituents of the atmospheres of those exoplanets. So we're looking for things like carbon dioxide in the atmosphere. Can we find one of those planets that has an atmosphere that is, for instance, similar to Earth? Or would it support carbon-based life, for instance? And this technology is essential and critical, and the enabling factor that enables us to basically look for life on other planets.
So I probably have to ask the question, do you think that we'll find life on other planets?
Well, I'm actually involved in another project now called Breakthrough Starshot, which intends to send a lightweight probe to Alpha Centauri by accelerating a sail, a light sail, with a very high-powered laser. It will take 20 years at 20% the speed of light to get there, but it's an investigation into whether the technology is able to support such a thing right now. That whole effort is really aimed at finding life elsewhere. And what's amazing is we haven't found it yet. So it really, on the one hand, it makes you think, are we in such a unique situation here on Earth that life just, the conditions just aren't right elsewhere? But on the other hand, if you look at all the opportunities for it to be right in the universe, or even our own galaxy, the Milky Way, you kind of have to go with the statistics and the odds and say, yes, surely there must be life somewhere else. And there might even be intelligent life. But, one of the things that intelligent life here on Earth hasn't been around very long. The universe has been around for 13.5 billion years. So, it's a small window, right? Where, we've come up, we've become intelligent, and now we're so intelligent that we're, maybe destroying our planet. And so if we end our civilization at some point, how long will it have lasted? Not very long compared to the age of the universe. And so being able to find another form of intelligent life that exists simultaneously with ours may be very, very small probability. I mean, it's a lot of stuff to think about. And I was kind of mind boggled the first time I was able to image an object with my 4-inch telescope in my backyard that sent light toward that telescope at a time before the sun existed, before our solar system existed. And it just kind of makes you stop and think and try to imagine what's going on. And it's just, mind-boggling.
Certainly, the idea that you saw something that passed by your telescope before the sun even existed is crazy.
And I think what's cool too about that is like on the obverse is thinking about other folks. Let's say there are other intelligent species looking back at our planet. They're looking at the same refraction where they're like, hey, we're going to see what this looked like 65 million years ago. They're seeing large dinosaurs, other creatures like traipsing across the planet and thinking, hey, this may not be what we see currently, but that's what the way the Earth appears to them. So it's crazy to think what others might be seeing had they been looking at Earth wherever they may be.
Yeah, that's right. We recently had an object come through our solar system that was from outside our solar system. And it had a weird shape and it had certain characteristics. And a few people actually believe was, an extraterrestrial intelligent, built by some intelligent life form, because it didn't really match some of the naturally occurring objects that we're familiar with that we see in our solar system. So, but it could have been from billions of years ago. If that were really true, I mean, it could have been from some dead civilization.
Yeah, if that were the case, I mean, we talked about it in the beforehand, or many people are discussed. It's kind of like Voyager, sending it out there and seeing who knows who's going to find it when. If humanity's still here, like you mentioned, or maybe we've already populated the stars and we'll find it later on. Like, hey, this is a time capsule of a time far, far before our own. And to think about the vastness of space and how, like you mentioned, something can travel for billions of years, it sets it into a different perspective. A lot of the work we're doing up there, it's a very long form, to say the least.
Yes.
Which, speaking of the modern, like where we're at now, though, kind of catching up, what is some of the current work you're doing now then with AFRL? Are you still working with the Starfire optical range, or what does your day-to-day kind of look like?
Yeah, I'm still working out at the SOR, but very sparsely. I'm just sort of staying on as a part-time technical advisor and consultant to various projects, and reminding people that, we tried that in 1997 and it didn't work, things like that. It's hard for me to let go because I put my heart and soul into the place and built a really great team of people. And it's the people that matter so much. And working with them and seeing their successes and progress. So I have that sort of connection, and hope that continues. As long as I'm making a little bit of a contribution and having fun, I'll keep doing it.
Well, hey, we can definitely say you've made a big contribution, because one thing we didn't want to, we'd be remiss not to ask is that you've had not only an asteroid named after you, but the very hill the Starfire optical range operates on bears your name. So we kind of want to know, now that you, like you said, you've been more of a mentor now and you're here helping out folks to keep this team together and answer questions. I mean, how does it feel to have that big an impact, especially in the area? Like, having these names honoring you, I mean, has to feel awesome.
I guess so. I certainly appreciate it. I think the thing that I'm just really, every time I see, for instance, in the news, in the science news, the reporting of some new discovery by astronomers, if I start digging into that, I usually find out that they made the discovery because they were using adaptive optics or laser guide star adaptive optics. And that is so gratifying to me to see that we're learning so much about our universe and our place in it just because of that technology, and having had a role in getting it to work and transitioning it to astronomers is very, very gratifying to me.
As it should be. Again, like, there's a reason that there's so many people want to honor your name, and especially the team you worked with, because it's well more than deserved. And to see, like you said, the impacts it's still having here, even though it's only been out for a couple of years, I mean, we know this is really going to keep changing things down the road, and hopefully someday find that exoplanet where we can all go hang out and party.
Yeah, that's an interesting concept, and getting to these places is not going to be easy.
No, you're absolutely right. And something I kind of want to talk about there too, like, speaking of these awesome places out there above our heads, a conversation that we had before that I think would really interest people is this idea of astrophotography, something that you very much enjoy and are very well known for. So can you kind of talk about what it's like to get into astrophotography for folks who may think it's intimidating?
It's a broad spectrum of what you can do. I mean, if you have a DSLR or a mirrorless camera, you can start by just setting it on a tripod and making short exposures. You can get some great shots of the Milky Way. It helps to be in a dark location. You basically want to manually run the camera. You manually focus the lens. It's best to have a really fast lens, so like a prime lens, for instance. And that is a simple way to get started. Don't try to do really hard stuff at once. Just start simple. There are so many resources on the internet now for helping getting started. Another suggestion I would have is to find an astronomy club and talk to them. Go to a star party. Astronomers quite often get together and set up their telescopes and compare notes, and a lot of that is visual observing, but some of the folks do astrophotography as well. That's, I think, a very useful technique, is to get with an astronomy club, and they're more than willing to help you and to explain what they do and what they've learned.
Yeah, and for our listeners, I think we're going to try to at least provide some examples of some of the amazing images that you have captured in our show notes on our website, the Lab Life podcast landing page on afresearchlab.com, so they can really just see, because these are, Ken loves puns, he would say out of this world, but yeah, great stuff.
I just am continually amazed at, nature's art. I mean, if you just look at these as a form of art, it's just amazing.
And something we kind of wanted to round the podcast out with, me being a very, kind of like we talked about earlier, like sci-fi, fantasy, things that really help inspire people to get in their fields. I'm a bit of a sci-fi geek myself, as many of the listeners know. And I think from what you mentioned at the top of the podcast, it's so important that a lot of people in the science community and folks that get interested start like listening or watching or reading sci-fi novels and just meet the medium itself at a young age. So can you talk about what the importance you feel that the genre has on scientific-minded people? And do you have any books or anything you'd say you'd recommend for folks who kind of want to get in the same headspace you may have, or kind of help garner your interest in the genre?
I haven't recently, I guess since I actually started working full-time, been into the science fiction community much. But back in the 1950s, when I was, a kid, it was a big deal. And the typical names that come up are Arthur C. Clarke, of course, Isaac Asimov, Ray Bradbury, Robert Heinlein. Those are the big names I remember. Arthur C. Clarke wrote, the one that had a really big impact on me was Childhood's End. And it was kind of contemporary, in that it starts out the 1945 to 1950 era with the U.S. and Russia sort of Cold War scenario. And then suddenly these aliens show up and sort of transform everybody's thinking. And the big impact, was how it changed the children and transformed their thinking through their dreams, basically. And eventually, they got to the point where they'd like to go off with these aliens. And I still have on my shelf the first edition of Childhood's End. It's all, kind of wasn't printed on really great paper and stuff, so it's getting kind of old and brittle, but it's one of my fondest possessions today. The other thing is, like Ray Bradbury, he wrote a book called The Martian Chronicles, and it was about a man leaving Earth and going to Mars and actually encountering a civilization there, an old dying one. But it's kind of relevant to today. Because today we're talking about going to Mars, and so the interesting thing about some of the old science fiction stuff is some of it is becoming reality, and I think there's some lessons to be learned. Isaac Asimov wrote a series of books called Foundation, and it was about scholars and scientists trying to save the future. A lot of the science fiction was about the situation that civilization was in, and what might be done to fix it, to make it better, or to escape from it, or whatever. So one thing about it is it makes you consider and think things through more thoroughly.
I completely agree. I mean, I'm glad you mentioned it. My favorite sci-fi novel outside of Frank Herbert's Dune will always be Childhood's End. So very cool plug if people haven't already read it. And definitely make sure if you want to be inspired, like you said, and think about things a little differently and possibly dream of the future, sci-fi is a way to do it. So we want to thank you for joining us, Dr. Fugate. It has been such a pleasure talking to you and such an awesome conversation. So thank you again.
Okay, it was great to be here, and thank you so much for having me.
Yeah, it was a real privilege. And for our listeners too, you gave us an AFRL Inspire talk in 2015, and we're also going to link to that into the show notes so they can hear even a little more of your story.
Okay, thank you.
Make sure to follow us on social media at Facebook, Twitter, LinkedIn, Instagram, and YouTube at AF Research Lab. And remember, stay curious.
Logging off.